Keeping this form, we now rearrange the numerator. Here denominator is x minus a. Therefore, for applying distributive law of division, I first arrange this. You note how I am arranging. Now in both the cases we are getting this form. This will be equal to g dash a and this will be equal to f dash a. That is second order derivative or third, fourth, etc. That means a more ordered derivative. First of all, second order derivative. From the name it is clear that after obtaining first order derivative, or you can say dy dx or f dash x, we have to find second order derivative. That means you have to differentiate that function you have obtained in case of first order derivative with respect to x, and that is second order derivative. Or higher order first order derivative, say of the function y equal to fx. First order derivative second order derivative, that is derivative of the derivative obtained earlier, ddx of dy dx, that is written in short other forms are other symbols or notations y2 if we use y, here I have used D2, capital D2, where capital D is ddx. And if we use f form, f dash x, that is the first order derivative, then second order derivative will be f double dash x or d2f dx2. These are the notations or symbols of second order derivative. Now the definition of second order derivative. d2y dx2 limit h tends to 0, f dash x plus h minus f dash x whole divided by h. And already it is mentioned earlier, h is delta x, that means change in x. In case of first order derivative, dy dx is the limit where h tends to 0, f of x plus h minus fx divided by h. Therefore, in case of second order derivative, this is the definition. And at x equal to c, that means at certain point the derivative is denoted by this symbol is equal to limit h tends to 0 f dash c plus h minus f dash c divided by h. This is the definition of second order derivative of a function y equal to fx at certain point x equal to c. Now, as this is a limit, therefore existence of second order derivative of a given function depends on the two limits, left hand limit as well as right hand limit. If those limits be finite and equal, then we say second order derivative at this certain point x equal to c will occur, and for that the limit when h tends to 0 minus, that is called left hand derivative, and the limit when h tends to 0 plus, that is called right hand derivative. We express that by writing this derivative exists if L f dash at the point C be equal to R f dash C, of course finite. In the next episode, I shall discuss sums of second order derivative as well as differentiability. I am going to continue derivatives. Till now, I have discussed all related theorems, results, and derivatives of standard functions as well as second order derivatives. Today, I shall work out few sums on derivatives, first order as well as second order, also derivability or differentiability. First of all, I have written one sum. If function fx is differentiable at x equal to a, then we have to prove this one. Since fx is differentiable at x equal to a, therefore f dash a is equal to limit h tends to 0 if a plus h minus f h. Now if we replace this is the condition of existence of derivative of the function fx at x equal to a, then in that case f dash a will be this one. Now if we change this h by x minus a, then the changed form is limit x tends to a if x minus fa by x minus a. This is the alternative form I have deduced from it. Now this result is to be used in this case. We start from the left hand side. Now keeping this form, we now rearrange the numerator. Here denominator is x minus a. Therefore, for applying distributive law of division, I first arrange this. You note how I am arranging. In place of x, I have written x minus a. The product will be then x into fa minus a into fa. But a fa is not there in this expression. That is to be adjusted. Carefully note the steps. Not so difficult thing. For division, here the divisor is x minus a. Keeping that in mind, I write in place of x fa, x minus a into fa. Then a fa is minus a fa rather is in excess. For adjustment, I have added a fa. Then the remaining one. Now limit x tends to a, x minus a whole into fa divided by x minus a. Applying distributive law. Then from it, if I take minus a common factor, then I get fx minus fa. For that, minus a fx minus fa divided by x minus a. Students or those who are learning in the initial stage of class 12, note carefully the arrangement, the trick I have used here. Keeping in mind first this one, I have arranged like this given expression. Now, the first one in the first fraction, x minus a will be cancelled. Since x tends to a, therefore x minus a is non-zero. Keeping that matter in mind, within brackets you mention since x is not equal to a. Below this, we will mention that minus a into limit x tends to a fx minus fa divided by x minus a. Limit x tends to a, say gx plus hx, that is equal to, as per the theorem of limits, limit x tends to a gx plus limit x tends to a hx. I have applied that, and since fa is constant, therefore limiting value will be fa. Now limit extends to fx minus fa by x minus, already we have written that f dash a. That is the RHS part proved. Next sum. Limit extends to a, numerator gx into fa minus ga into fx, denominator x minus a, that will be equal to 5. Given this condition, fa2 ga minus 1, f dash a1, g dash a2. Keep it in mind this form. This form is to be used also here. Now gx is there. If I take gx minus ga, then I get this form, gx minus ga whole into fa. That fa part or ga part is to be adjusted. Follow that. Now after multiplication we shall get the first term as gx into fa, this one. Now the second term will be minus ga into fa, but it is not here. For that we have to add ga into fa minus ga into fx. Now you see, in the next step we shall take ga common factor, so that we shall get fa minus fx. If I take minus ga common factor, then numerator will be fx minus fa. Now x tends to a, gx minus ga whole into fa divided by x minus a. Keeping that form in mind, minus we take ga common factor, fx minus fa by x minus a. I keep third brackets. Then two limits as per the formula. Limit extends to a, fx plus gx is equal to limit extends to a, fx plus limit extends to a, gx. Those are the theorems. Also you can call formula. Then fa is constant here, therefore fa will be outside the limit minus ga is constant, now in both the cases we are getting this form. This will be equal to g dash a, and this will be equal to f dash a. Now we put the values already given, these values. Therefore, LHS equal to FA equal to 2, G dash A equal to 2 minus GA, that is minus 1, GA equal to minus 1, F dash A, that is 1. That is equal to RHS. Now I have chosen this sum to discuss the continuity and differentiability of this function. Actually, in our syllabus we have continuity as well as differentiability. I shall discuss both cases for this sum. For continuity, let us recall the condition. A function fx will be continuous at the point x equal to a if left hand limit, that is LFA, is equal to right hand limit, that is RFA, is equal to FA. For that, also for differentiability we need the value of FA. For both the purposes, we first find the value of F1 and F2 from the given condition. If 1, that is to be determined, students, you see these intervals. Here x lies in between 0 and 1. Here x lies in between 1 and 2 along with the extreme values, that is at x equal to 1 and 2, and this is for x greater than 2. For getting f1, we have to use the value of fx, this one, as in this case interval is 1 less than equal to x less than equal to 2. Therefore, putting x equal to 1 here, we get f1, 2 minus 1, that is equal to 1, and f2, that will also be determined from that, 2 minus 2 is equal to 0. Now, limit x tends to 1, fx will exist, fx will exist if F1 is equal to Rf1. Lf1 is equal to limit x tends to 1 minus fx. That means just less than 1. Limit x tends to 1 minus less than case, that means the function will be x, that is equal to 1. Rf1 limit x tends to 1 plus fx greater than 1 case, that means this one just greater than 1, limit x tends to 1 plus value of fx will be in that case 2 minus x, that is 2 minus 1 equal to 1. As already we have got that value f1, f1 is also 1, therefore f1 fx is continuous at x equal to 1. I make, after writing this, L f1 is equal to R f1 is equal to f1. Condition of continuity of fx at x equal to 1. Fx will be continuous, therefore continuous at x equal to 1, therefore left hand limit equal to right hand limit equal to value of the function at x equal to 1, and we find all these three values are equal, therefore x is continuous at x equal to 1. Now I suggest students who are practicing, you find for x equal to 2 the continuity case of fx at x equal to 2 yourself. Now I discuss the differentiability at x equal to 2. It is suggested that you yourself follow these steps and show the continuity of fx at x equal to 2. I am discussing the differentiability of fx at x equal to 2, not at x equal to 1. That will be done by yourself. Of fx at x equal to 2. Now I am discussing this one. Fx will be differentiable at x equal to 2 if L f dash 2 is equal to R f dash 2. Now L f dash 2 is equal to limit x tends to 0 minus f2 plus 0 minus f2 by 2 plus h by h. Limit h tends to 0 minus f of h plus 2 minus f2 by h. Now f of 2 plus h and h tends to 0 minus, that means we are adding a number just less than 2. Just less than 0. That means negative. That means 2 plus h is finally less than 2. For that, limit h tends to 0 minus less than 2 case, we have to consider this one. f of 2 plus h will be found from this one. That means in place of x we have to put 2 plus h. 2 minus 2 plus h minus f2, that will be obtained from this same condition f2. Okay, let me find that f2 equal to 2 minus 2 equal to 0. Note carefully, students. Numerator is f of 2 plus h minus f2, and you see h tends to 0 minus, that means h is just less than 0 means negative. That means 2 plus h, 2 plus a small negative number, that means that will be less than 2 finally. For that, to determine the value of f of 2 plus h, we have to use this condition. From that, 2 minus within brackets 2 plus h. Finally, therefore, L f dash 2 is equal to limit h tends to 0 minus 2 cancelled minus h by h, that is equal to minus 1, since h is not equal to 0. H tends to 0 minus, that means h is non-zero. Therefore, we can cancel these two h from the numerator and denominator. Therefore, we shall get minus 1. Now, we calculate R f dash 2. Limit h tends to 0 plus f of 2 plus h minus f2 by h. Now we note h tends to 0 plus, that means a bit greater than 0, that means positive. Therefore 2 plus h is greater than 2, 2 plus h greater than 2. We have to find, in that case, f of 2 plus h, that means we have to use this condition, x greater than 2. Therefore, f of 2 plus h will be obtained by substituting x by 2 plus h in this expression. Therefore, limit h tends to 0 plus, from here 2 plus h minus half 2 plus h whole square. I have substituted 2 plus h in place of x. This minus f2, already we have got f2 equal to 0 by h. Now we calculate limit h tends to 0 plus 2 plus h is common factor, 1 minus 2 plus h by 2 whole divided by h. R f dash 2 is equal to limit h tends to 0 plus, after simplification, in this case 2 minus 2, 2 will be cancelled, then minus h, 2, that is at the denominator I write here 2h, numerator 2 plus h into minus h. See the simplification. Denominator will be 2, numerator will be 2 minus 2 minus h, so 2 are cancelled, finally minus h. Now h is cancelled since h not equal to 0. Now finally we shall put h equal to 0, therefore minus 2 by 2, that is equal to minus 1. Therefore L f dash 2 is equal to R f dash 2, which implies fx is differentiable at x equal to 2. Already I have mentioned that you yourself find the differentiability of the function, given function at x equal to 1, as well as continuity of the function, same function at x equal to 2. I have shown 2 cases. You are to solve yourself the other 2 cases. In this case, we find fx is continuous at x equal to 1, also differentiable at x equal to 2.